Hello, welcome to lecture 41 of analog integrated circuit design. We have been discussing fully differential op amps. Fully differential circuits have a lot of advantages like immunity to noise and also that they cause less noise and interference to other circuits. So, that is why most of the circuits today are fully differential. Now, when you make a circuit fully differential, you need to have a common mode feedback loop to stabilize the output common mode voltage. Okay. This is true of any circuit that you can think of, and every circuit that we have discussed so far can be turned into a fully differential version like the transconductor or the single stage op amp, two stage op amp, three stage op amp, anything that you take. Okay. But each of these stages needs a common mode feedback circuit, and sometimes like let us say a two stage op amp may need two common mode feedback circuits, one for each stage of the op amp. So, we need to understand common mode feedback circuits very well. We will first do that with the single stage op amp, because the single stage op amp circuit is simple. We can discuss a number of ways of accomplishing common mode feedback in that circuit, and then we can translate that to any other circuit that we want to build. Okay. Now, there is a great variety of common mode feedback circuits. Just like in any other circuit, just like op amp topologies, there is a huge variety. We will not be discussing all of them, but we will discuss a few interesting cases, and you can consult the literature and textbooks for other possible common mode feedback circuit variants. Okay. But the basic principle behind all of them is the same. You will always have two current sources sort of fighting each other, one current source at the bottom and another at the top, and this is necessary in order to have a very high impedance, which is what gives you a very high gain. Okay. But if you just leave it like that, because of small mismatches in the current and the high impedance, the voltage will either go to somewhere near VDD or somewhere near ground, and the transistors will no longer work in saturation region. We have to establish the common mode or the bias voltage at some desired value somewhere in the between the supply rails, so that the transistors are in saturation, and that is why we have the common mode feedback circuit. So, the job of the common mode feedback circuit is to adjust one of the current sources using negative feedback, so that it exactly matches the value of the other current source. Now, when I say one of the current sources, we do not mean individual current sources, but the sum of the current sources in the two differential arms of the circuit. Okay. Now, another way to think of common mode feedback circuits is that it provides a low impedance in the common mode. What is meant by common mode and differential mode? If you apply two signals, either voltages or currents of equal magnitude and opposite sign, that is differential mode. If you apply two voltages or currents of equal magnitude and the same sign, that is common mode. Now, when you apply a common mode signal, it should appear like a low impedance circuit, and when you apply a differential mode signal, it should appear like a high impedance circuit, because for differential signals we need very high gain. Okay. This is our single stage op amp, and the voltage here at the gate of M3 and M4 controls the values of the current sources from the top, and at the tail I have assumed a fixed current source I naught. Now, the common mode feedback can be used to either set this voltage or this voltage, so that the tail current is adjusted. In this particular case, I have assumed that the tail current is fixed and we are adjusting the value of the current from the top. Okay. Now, a general representation of common mode feedback circuit is like this. We have a common mode detector, that is, we have something that measures the common mode voltage, compares it to a desired common mode voltage VOCM, and continuously increases or decreases the gate of M3 and M4 in a direction such that the detected common mode voltage converges to the desired voltage VOCM. Okay. It is a classic negative feedback circuit. Now, in this particular circuit, because increasing the gate voltage reduces the output common mode voltage VOP plus VOM by 2, the signs have to be of this for this particular op amp. Okay. We also saw a very simple realization of this circuit, where we did not have an explicit op amp for comparison. All we had was we made a common mode detector using a resistive divider of equal resistors. Okay. The midpoint will be at VOP plus VOM by 2, and you simply connect it to the gates of M3 and M4. Now, in this particular case, the output common mode voltage will be stabilized to the gate voltage of M3 and M4 at a drain current of I 0 by 2. Okay. When you apply a differential voltage, what happens is that VOP will swing up, let us say, and VOM will swing down by an equal amount. The average value does not change. Okay. So, the common mode feedback circuit does not react to differential signals. That is a prerequisite of the common mode feedback circuit. It should not react to differential signals. Okay. The same thing happens here. If VOP goes up, VOM goes down by an equal amount, this voltage does not change. So, the currents delivered by M3 and M4 do not change at all. Now, the only problem with something like this, a resistive common mode detector, is that it will always load the op amp, okay, or whatever stage we are detecting the common mode of. Now, the advantage of a resistive common mode detector like this is that it is more or less ideal. If you have VOP and VOM, here we get VOP plus VOM by 2, and first of all, because we use resistors, it is linear even for large swings of VOP and VOM, and also its range is not limited. Okay. By itself, VOP can swing to any value and VOM can swing to any value, and the midpoint of this will still be VOP plus VOM by 2. Okay. But the disadvantage is that in the differential picture, keep in mind this midpoint will be ground. So, we will have this in the differential half circuit. Okay. So, from the output to small signal ground, there will be a resistance R, which will load the differential circuit. Okay. So, while the resistive common mode detector is more or less ideal, it loads the differential circuit, that is one disadvantage of it. For instance, if you use it in a single stage op amp, it will reduce the gain. Okay. So, in order for it to not reduce the gain significantly, the value of R must be as high as possible. Now, there may be practical problems in achieving this, because if you want a high resistance, you need to have a very long and skinny resistance, and that may take up a lot of area. So, that could be one practical problem. Okay. And in any case, even if you make a large resistance, you may not be able to make it much larger than the RDS of the transistors. If you have a resistance R that is smaller than the RDS of the transistors, the DC gain will be dependent on R and not on the RDS of the transistors. Okay. In either case, you will not be able to achieve the maximum gain that is possible in a single stage op amp. So, a resistive common mode detector is usually not used with the single stage op amp. Okay. So, that is one thing. Now, there is another issue. Let us say you go on making the resistance very large. Okay. What happens is, there will be a parasitic capacitance from the midpoint. This is VOM, VOP. Here I get VOP plus VOM by 2 at DC. Okay. Now, if you consider higher frequencies, let us say you go on increasing R just because you do not want to load the circuit. What happens is that in the common mode half circuit, let me draw the common mode half circuit of this. For that, I simply take, this is the line of symmetry, I simply take this side and fold it back on that side. So, I have a resistance R by 2 and Cp, and this is the detected common mode. Okay. So, here I have the common mode output and here I have the detected common mode, and it is clear that for higher frequencies the detected common mode is not the same as this, because this is a low pass filter. Okay. Now, this can also be a problem. Now, when we have this feedback loop, okay, if you have a pole in the common mode detector, that adds to parasitic delay. Okay. As we know, any parasitic pole adds to a delay in the feedback loop, and that can make the circuit unstable, that can make this feedback loop unstable. We have not looked at the details of this feedback loop yet, but we will do that soon. But in any case, you know that a negative feedback system cannot have too many extra delays. So, here the transfer function from this point to that point would be a first order low pass transfer function. Okay. So, if R is very large, obviously the delay is very large, or the bandwidth of this low pass filter is very small. Okay. Now, how do we fix this? We have earlier seen that by introducing a 0, we can essentially present an advance, that is a negative delay, and then counter the effect of the delay. Now, how do we implement a 0 in this first order low pass filter? That is very easy. All we have to do is to connect some capacitance like this. Let me just call that Cz. Now, in this particular case, the transfer function changes to, from A to B, it will be okay. So, at high frequencies, it will simply be that of the capacitive divider. Okay. It is easiest to think of this as the capacitor Cc is a short circuit across R by 2 at very high frequencies. So, all you have is this capacitive divider, you do not have the phase shift due to this RC circuit, you simply have an attenuation, and the transfer function changes to Cz by Cz plus Cp. Okay. Now, if Cz is comparable to Cp, this is some number, some fraction of 1, okay, and that is quite acceptable as long as it does not give a phase shift. So, there are many ways to think about this. You can think of the 0 providing a phase lead or a negative delay, but in any case this can be used to stabilize the circuit. So, that means that in the actual circuit, remember this is only the common mode half circuit. So, in the actual circuit we need to have half of the capacitor across each of the resistor in the common mode detector. Okay. Now, this is fine, this can be done, but you see that this will also load the circuit. Okay. So, now in the differential half circuit, we will have this load as well. So, in addition to the integrating capacitor and the load capacitor of the single stage op amp, we also have the capacitance used in the common mode detector. Okay. So, the passive common mode detector is very useful because it is linear, but it has some problems. First of all, it loads the circuit, that is the main problem. Okay. But the advantage is that it is very linear. So, we will see that there are some situations where we will use this. and in some cases where we will try not to use this one. Okay. Now, what is the alternative? The one common thing whenever you are presented with a heavy load is to buffer it. Okay. So, that is one of the obvious solutions. What is a buffer? We can use a source follower as a buffer. I will show it with an NMOS source follower. You could also use PMOS if the voltage ranges are compatible. So, let us say this is VOP and VOM, and we have two source followers MC1 and MC2. So, this will be some VOP minus some fixed voltage, okay, VGS C1, and this will be VOM minus VGS C1. I will assume that for now there is no body effect in these transistors. So, the detected voltage here at the output will be VOP plus VOM by 2 minus VGS C1. Okay. So, it is related to the common mode voltage, but it also has a level shift which is the same level shift of the source follower buffer. Okay. Now, our circuit looks something like this. We had to compare the detected common mode voltage to the desired common mode voltage and feed it back to the current source transistors. Okay. I will simply label this CMFB. CMFB is nothing but this node. Okay. I am only concentrating on this part of the circuit here. Now, what happens is if the common mode feedback loop is stabilized, the detected voltage here and this VOCM will be equal to each other. After all, this op amp here is measuring the error between the two and changing the common mode feedback voltage until these two become equal. Now, this is a problem because VOP plus VOM by 2 does not equal VOCM, it will equal VOCM plus VGS C1. Okay. Now, this VGS C1 is an unknown quantity in that you can calculate it if you know the parameters of the transistor and the current exactly, but you do not know that. Okay. So, you would in general like to avoid something like this where you have the output common mode voltage dependent on some VGS that depends in turn on process variations. Okay. Now, this kind of situation occurs very commonly in IC design as well. You will have to deal with some quantities which in principle can be calculated, but because the parameters of the MOS transistors varies across process and temperature, these numbers also vary quite a lot. Now, a very common technique in IC design to counter these is to exploit matching. Okay. It is very clear that instead of comparing the detected common mode voltage with VOCM, if I compare it with VOCM minus VGS C1, I will get exactly what I wanted. VOP plus VOM by 2 will be equal to VOCM. Okay. What I mean is I should not do the comparison with VOCM, but VOCM minus VGS C1. Okay. Now, how do I obtain this VGS C1 in this expression? That is again very easy. I use a replica of this particular circuit. Okay. I will write that here maybe in a different color just to make that clear. So, let me call this MC1 prime and use the same current, let me call this IC 0, these are also IC 0. And I connect it up there, and the gate of this is connected to VOCM. Now, here what we will get is VOCM minus VGS C1 prime. Now, this stage is a replica of these two stages, source follower stages. So, VGS C1 prime will be equal to VGS C1. So, finally, when these two voltages become equal, it implies that VOP plus VOM by 2 equals VOCM. Okay. Now, this business of exploiting matching on integrated circuits is very common. Okay. We have used it for simple circuits like current mirrors. There are so many cases where you have two things to match very well, you have to match all the parameters. Okay. In that case, you simply use a replica circuit. Now, that sounds vague. I have shown you one instance of it. So, whenever you have let us say voltage drops or some other parameters dependent on MOS transistor characteristics, you may be able to use a replica circuit. So, that the dependence on MOS parameters, which is also process dependent, will be cancelled out. So, this buffered resistive common mode detector clearly does not load VOP and VOM, because looking into the gates of MC1 and MC2, we have high impedances. Okay. But the problem now is that initially when we had only resistors, the range was infinite. I mean, practically you could have a VOP and VOM of any values. Now, if VOP and VOM become very small, they will drive these current source transistors into saturation. You can find out for yourself what the limits are. ICO, these current sources are also implemented using MOS transistors, and similarly if it becomes very large, MC1 and MC2 will go out of saturation and into triode region. Okay. Now, that is not very likely, because for an enhancement transistor with a positive threshold voltage, VOP has to be above the supply voltage VDD for MC2 to go into triode region. So, that is not likely, but at least there is a lower limit. So, that is one problem. Okay. So, we will end up with some swing limits. Now, secondly, these transistors will have body effect. Okay. If you use PMOS, you can avoid it, but as I have mentioned earlier, even with a PMOS, tying the substrate to the source is not a very good idea, because it increases the parasitic capacitance at the source greatly. Okay. So, if you do have body effect, what happens is that this drop here is not a constant, as I have represented. It is not just VGS C1 on both sides. If VOP is large and VOM is small, the VGS of MC1 will be small and MC2 will be larger. Okay. So, the level shift will depend on the absolute values of VOP and VOM. So, you will get some nonlinearity in the detected common mode. Okay. Now, this is a very common effect with any active circuit, and with an active common mode detection circuit, the same problem will apply. But if you expect the swings here to be small, this kind of circuit can be used. Okay. Now, what is the problem with a nonlinearity in a common mode detector? The problem is that once the circuit becomes nonlinear, it will not react only to the common mode VOP plus VOM by 2. In general, it will be some nonlinear function of VOP and VOM. Okay. So, you will have some response to the differential component of the circuit as well, and that is not good. Now, it turns out that if you have some nonlinearity in a common mode feedback circuit, that will be an even order nonlinearity because of the symmetry of the circuit. An even order nonlinearity combined with some mismatch in the circuit can give you even order harmonics in the outputs of the circuit. Okay. Now, this is a very general description. For details, you have to look at specific circuits, but what you can expect from nonlinearity in common mode feedback circuits and combined with mismatch in the differential part of the circuit is that you will have even order distortion. Okay. A fully differential circuit, it should have no even order distortion, but you can have it because of this reason. Now, as before, if R is very large, then there is a pole in the transfer function between the actual common mode VOP plus VOM by 2 and this point where you do the comparison, and you can reduce the effect of that pole by adding zeros using these capacitors. Okay. This is a summary of the buffered resistive common mode detector. Let me just show you the full circuit of the single stage op amp. draw it slightly differently from before. I will show these as current sources, but it is understood that you make them using MOS transistors. Okay. So, we compare these two and feed it back there. Okay. We will see how to make this particular op amp shortly. Okay. So, right now this is what the circuit is. And you can also see that in the differential picture, this point will be at ground and these two will in the ideal case offer no loading. In reality, because of CGS of MC1 and MC2, there is some small loading on the single stage op amp. Okay. I have not shown the integrating capacitors of the single stage op amp. Whatever load capacitance you have here will be the integrating capacitance, and so it is this part of it, that is the op amp, and this is the common mode feedback. Okay. And this implements a fully differential single stage op amp with a unity gain omega u equal to GM 1 by C and a DC gain, which is the GM of this transistor divided by sum of GDS of these two transistors. Okay. Now, we need to go ahead and implement that op amp. Now, we do not need a really fancy op amp there. So, we will start with the simplest op amp that we know, that is the single stage op amp. Now, notice that this op amp has a differential input and a single ended output. So, the single stage op amp that we analyzed earlier with the single ended output is what we are going to use. Let me change the notation a little here. I will call these transistors MC11 and MC12, and this is MC11 prime. Okay. And these are all equal to IC 11. So, the single ended single stage op amp looks like this. If this is the plus terminal and this is the minus terminal, that is the output, and the common mode feedback is completed like that. Okay. And all these upper lines are VDD. Now, first of all, one remark about this circuit. This is just a single stage fully differential op amp with common mode feedback. Already you see that the circuit looks very complicated with many transistors, and it is probably at the limit of what I can draw in this area of the screen. Okay. So, it is extremely important to understand what is behind the circuits. You cannot really mug up these circuits, you cannot learn them by heart and then figure out how they work. You have to be able to understand each part of the circuit and then understand the function of the circuit. Okay. Also there is a huge variety of circuits. I can change from NMOS to PMOS in most of the circuits. I can change the kind of common mode detector and so on. Okay. So, the most important thing is to understand the principles behind this common mode feedback circuit, or in fact any other circuit. Okay. Now, we have this common mode feedback loop, and like any other negative feedback loop, we have to make sure that it has a small enough delay and it is stable. Now, as far as the common mode feedback loop is concerned, we need to be concerned only with the common mode operation. So, I will use the common mode half circuit, that is, normally you would apply a differential input to this op amp, but I will now assume that we have applied only a common mode input and analyze the common mode part of it. When we want to analyze the differential part, we can do it using the differential half circuit. Okay. Now, keep in mind that this is the line of symmetry, okay, and this is the line of symmetry as well. So, these points will be at ground in the differential half circuit, and in the common mode half circuit I have to fold all of these circuits on top of each other in parallel. Okay. For instance, this R comes on top of that R, these two transistors will be in parallel, these two current sources will be in parallel and so on. So, let me draw the common mode equivalent circuit. When I write M1 comma 2, it means that M1 and M2 are in parallel and M0 appears as it is with a current I0. This is the common mode feedback node, M3 and 4 are in parallel there, and here I will have MC11 and 12 in parallel with a bias current of 2 IC0, because I have two current sources in parallel. I have the resistance R by 2, okay. And this part of the circuit, I will use the same color as before. Here I have the replica to generate the correct offset of the source follower. Okay. This is 2 IC11, sorry. And the current in this I will denote it by IC0, okay. And the common mode feedback circuit is completed from here, okay. So, this part of it, which is really the differential op amp, simply looks like a current source in the common mode equivalent circuit, okay. This is at some V bias, and this the bias for M0 is derived from some current mirror. I will just call it VG0. These two together form a cascade current source, okay. So, now if you look at this circuit, we have a differential pair, that is a single ended single stage op amp, okay. And the output of that goes to M34, and this output is from the drain. So, basically M34 acts like a common source amplifier. This is a common source amplifier, and the output of the common source amplifier goes to a source follower MC11 and 12. It has a series resistance R by 2, but let us now act as though it is not there, or assume that the frequencies are so low that no current flows through R by 2, because it is connected to the gate. So, we have a source follower. Okay. So, we have a single ended single stage op amp cascaded with a common source amplifier and a source follower in the feedback loop. Okay. The feedback loop goes like this, right. So, here we have it, and then the output of the single ended single stage op amp is like that, and then feedback loop gets completed that way. Okay. So, that is the feedback loop. Now, what do we know about the stability of this? If you observe this circuit, what we have is equivalent to a 2 stage op amp with an additional source follower buffer. Now, the source follower buffer came because we used a buffered common mode feedback stage. If we did not use that, even that would not be there. Okay. Because what we have in a 2 stage op amp is a single ended single stage op amp followed by a common source amplifier. Okay. So, the part that I have drawn in green plus the transistors M3, 4 will act like a 2 stage op amp, and it happens to have an additional source follower buffer MC11 and 12 okay, in the common mode equivalent circuit. So, whatever we discussed earlier for the stability of the 2 stage op amp will apply here as well. Okay. Now, we know that in order to have stability in the 2 stage op amp, we needed to have a Miller or integrating capacitor from the gate of the common source amplifier to its drain. Okay. So, this is what was called CC, and because it is here for the common mode feedback loop, I will call it CC-CM. Okay. This is what makes this GM and this C behave like an integrator. Remember, what we need here is an integrator. Now, what we have not implemented is not an integrator by itself, but a transconductor, and this transconductor in combination with the CC-CM behaves like an integrator. Okay. Now, another way to think about it is that there are too many stages in feedback loop. So, there is a lot of parasitic delay. So, one of them has to dominate, right, one of the delays has to dominate, that is what we call by dominant pole compensation. So, the feedback has to be closed around a single stage, and that can be done by using this capacitor. Okay. So, any way you think about it, essentially you will have a single stage in feedback. Okay. And also, as I mentioned earlier, if this R by 2 is very large, then this R by 2 in combination with the CGS of MC1 will cause a lot of delay in the loop. So, you may also have to connect a capacitor, so that it creates a 0 in the loop. Okay. So, this is what we need in order to have a stable common mode feedback loop. Now, you see that the circuit looks exactly like the 2 stage amplifier, where the CC-CM is the integrating or the Miller compensation capacitor. Okay. And just like with the 2 stage op amp, you can also add a 0 cancelling resistor in series with this. Okay. Now, please do not get this confused with the op amp that we are trying to realize. We are trying to make a fully differential single stage op amp. Now, the common mode feedback loop for that op amp looks like the single ended 2 stage op amp. Okay. Now, because we have already analyzed the single ended 2 stage op amp to a great detail, we do not have to reanalyze that here, we just have to associate the terms here with what we used over there. Okay. Let us recall that the 2 stage op amp had a topology like this. Now, in addition to that, we have a buffer. Okay. We also have parasitic capacitances here and there. Okay. Let me just call it C3 and this is C. Now, this GM1 we know is not a memoryless GM1, but it has a pole and a 0. Okay. These are the results that we have already derived for the 2-stage op amp. You can go back to those lectures and revise it if you wish to. Now, this part corresponds to whatever I have drawn in green in the previous picture. So, that is the single ended single stage op amp, and this GM2 and the second stage corresponds to this M34 and this integrating capacitor, possibly with something that cancels the right half plane 0, and finally, this buffer is made using that. In addition to all of this, we also have this in the loop. Okay. So, you see that the loop is completed around this entire thing. This loop is an unity feedback. Okay. So, what we need to know is which components are associated with which part of this, and if you wish to, you can put down the values of GMs and calculate the where the poles and zeros are and ascertain if the circuit is stable. Okay. Now, the unity gain frequency of this feedback loop, which is also the unity loop gain frequency, because we have unity feedback around this, will be GM1 corresponding to this divided by C. Okay. Now, translating the terms, it will be the GM of these transistors GMC1 divided by this capacitor here, the integrating capacitor CCCM. Okay. The unity loop gain frequency of the common mode feedback loop is GMC1 divided by CCCM. Okay. Now, there are a number of poles and zeros. So, we will have the mirror pole and 0 due to the first stage, it will be at GMC3 divided by some parasitic capacitance associated with that, that is where the pole is, and the 0 will be at twice that value. Okay. All these results you can recall from earlier analysis of the single stage op amp. In addition to that, we have the second pole due to this GM2 and the load capacitance. Okay. Very crudely, it is GM2 by C3 plus C1, but we know it is not the case. GM2 will be divided by some factor and so on. So, you can work out the calculation, and there are also basically poles at associated with this node and poles in the buffer, and also due to this resistive element here. Okay. So, there will be a number of poles and zeros. We have to make sure that the phase lag due to all of these poles and zeros at the unity loop gain frequency is, let us say, less than some value. So, 30 degrees or so, so that you have a healthy phase margin. Okay. Now, in practice, what you do is not to sit and calculate all of this analytically. You need to know which of the components contributes to poles and zeros, so that you can manipulate the values if you need to. Okay. If necessary, you can change the poles, that is, move the poles to higher frequencies and so on. But generally, once the circuit becomes so complicated, these hand calculations will not be efficient. So, we will go to a simulator. In one of the later lectures, I will show in detail how to design an op amp using the simulator, and how to measure the loop gain and so on, so that you can have a sufficient phase margin. You can design the feedback loop to have a sufficient phase margin and limited ringing in the step response. Okay. So, for this, what we will do is put this circuit in a simulator, and there are ways to measure the small signal loop gain, and there are also ways to measure the step response you will do that and make sure that the stability is guaranteed. Okay. When you carry out such an exercise and find out that the phase margin is not sufficient or there is a lot of ringing, you will need to know which components to change. Now, the analysis that we have done earlier is useful for that. Okay. So, you should know which components are contributing to the poles and zeros, so that you can change that part of the circuit and improve the phase margin. Okay. So, in summary, the common mode feedback circuit is required stabilize the output common mode voltage of fully differential circuits. Okay. Common mode feedback circuit consists of a common mode detector plus some transconductor or op amp to complete the feedback. Okay. Sometimes these transconductor to compare the detected common mode to the desired common mode is not explicit, but it is implicit within some part of the circuit. Okay. Now, the common mode feedback loop, which basically is the common mode equivalent circuit of the complete op amp, must be stable, of course, like any other feedback loop. And here by stability we mean not only not oscillating, that is not merely having poles in the left half plane, but also limited amount of ringing and overshoot. So, the common mode equivalent circuit can be anything. Now, for the particular case that we considered, and this is a fairly typical case, single stage op amp plus a buffered CM detector plus a single stage transconductor single stage single ended transconductor for CMFB. Okay. Now, in this case the common mode feedback loop itself looks like a two stage single ended op amp. Okay. And you have to analyze this usually with a simulator and ensure that it is stable. Okay. Now, if we go back to the very simple common mode feedback we had earlier, all we had was this R connected there, there will be invariably be some parasitic capacitance at this node due to these transistors as well as maybe due to the resistors. Okay. The common mode equivalent circuit of this is okay. So, there may be some parasitic capacitance here, I will call it CP3, and then to make this into an op amp we will have the integrating capacitors C. Okay, we will have that. Now, in this feedback loop, which is basically that one, the combination of M3, 4 and these capacitors, sorry, this should be 2C in the common mode half circuit, common mode equivalent circuit. So, this transistor and these capacitors behave like an integrator, and this resistance in combination with CP3 will be a parasitic delay, which can be reduced by adding a capacitor Cz. Okay. Now, because we have one integrator and a single parasitic pole, it is quite easy to stabilize this one, okay, compared to the other case where we had a 2-stage op amp. Now, the common mode feedback loop in this particular case is equivalent to a single stage op amp, and the common mode feedback loop when we have a more elaborate common mode detector is like a 2-stage op amp. Okay. Now, this is a fairly typical case and you need to be able to work with this, but because we have analyzed the 2-stage op amp in great detail, you should be able to work it out. I am not going to write the expressions for poles and zeros here. I am assuming that you can associate these components with the components in the 2-stage op amp. Similarly, here the integrator is the GM of M34, that is 2 times GM3 divided by 2C. That will be the unity gain frequency of the integrator in the common mode feedback loop. In any feedback loop, you will have some integrator like behavior, and you will also have parasitic poles and zeros in the circuit. You just need to make sure that the effect of all those things is such that the phase margin is sufficient, that is there is not a significant phase lag at the unity loop gain frequency. Okay. This is the unity loop gain frequency of the common mode feedback circuit. See you in the next class. Thank you.